4.5 is an algorithm for curve sketching. So what we're going to do is we're going to take all of our skills that we've learned in this chapter and in previous chapters, previous years, and we're going to create an algorithm to help us curve sketch any function, any rational function, polynomial function, whatever the case may be. Okay, so this algorithm is a combination of a few things. First of all, when we talk about curve sketching, a lot of guys think that this is outdated. Why are we curve sketching? We have graphing calculators, we have Desmos, we have computer software. We curve sketch to understand functions more qualitatively. So we understand what's happening at particular aspects of a function once we graph it. And as you get better graphing it, you'll get faster, and you'll be able to recognize certain aspects of the function quicker. So when you have something complicated, your brain can kind of organize itself and analyze critical points in that graph, maximum, minimums, better than someone else. So it's more about understanding functions than it is about actually sketching a curve. Of course, we have computers to sketch curves, right? We know that already. Okay, so what info do we have? Info that we have or that we can use. Okay, number one is domain. We want to know if there's any discontinuities in the domain. We want to know if x is an element of all real numbers. Maybe it can't exist somewhere. This is our first step to understanding what we can draw, because if we don't know where we can draw, we can't even start. So number one is going to be domain. And coming from domain, we're also going to understand our asymptotes. Do I have vertical asymptotes? Do I have horizontal asymptotes? I need to find out where my asymptotes are, and I know we know how to do that already. And we also need to know the behavior on either side of the asymptote. Okay, maybe we want to plug in some values on one side of the asymptote, on the other side, just to see where it's approaching. Is it approaching infinity? Is it approaching a certain value? So that could help us. Okay, number three is intercepts. Intercepts are really easy points to come up with, whether it's the y-intercept, which is extremely easy. So the y-intercept and the x-intercept. Or it could be the x-intercept, which generally involves factoring and figuring out when the numerator or the whole function equals 0. Okay, so if I can find x-intercepts and y-intercepts, those are a lot of points that I can anchor my graph on. Okay, number four. By the way, these are all from kind of last year or even advanced functions. Nothing new here so far. The new thing is critical points. Okay, we want to find all the critical points because this tells us our intervals of increase and decrease, or when those happen, if there's a max or a min somewhere. So what we want to do is we want to find the first derivative and when this equals 0. Okay, this will help us find local extrema as well. Okay, so if I have local maximums and local minimums, I know where this graph is going to turn around, right? Because I'm going to find out when the slope of the tangent is actually 0. So if I have all these horizontal slopes, I know that these are max and mins. So I can curve and turn directions when I'm curve sketching. Very, very important. Okay, and likewise with the first derivative, we have inflection points with the second derivative. Okay, so we want to find out when the second derivative is equal to 0. Okay, and we can also remember concavity here. Okay, so we want to find out when the second derivative equals 0, because this is going to tell us whether it's concave up or concave down. Now, we can use all of these together or some of them together to kind of get a general idea of how we're going to graph this function, the shape it's going to take, the points it goes through, the points it can't touch. All these things are going to help us with a graph. There are the sixth one I'm going to write over here, but I'm not too sure I'm going to get too into it. It's going to be oblique asymptotes. Okay, so if I have an oblique asymptote, which is a slanted asymptote, generally it's the equation of a line. When the numerator has one more degree, exactly one more degree than the denominator, we just divide those functions, we find our oblique asymptote, and I want to know the behavior above and below this oblique asymptote. Okay, same as the other asymptotes. Okay, so here we're going to start with a regular polynomial function. I've listed the 5 main points for the algorithm over here. And we want to sketch negative 3x cubed minus 2x squared plus 5x. Okay, so the first thing we're going to do is we're going to look at the domain. So this is a polynomial function, and if you know something about polynomial functions, is the domain is xer. There's no restrictions on the domain. There's anything I can plug into x, right? I don't have an x at the bottom like a rational function. I don't have an x in a root, so I can't have a negative x. Anything goes over here. So I have xer here for the domain. Domain done. Okay, now asymptotes. What asymptotes do I have in a polynomial function? None. Amazing. My favorite answer. Okay, now 3 intercepts. I'm going to find the y-intercept. Okay, because that's when x equals 0. If I plug in 0 into this function, my y-intercept is 0, 0. Okay, that's done. I'm going to go over here and I'm going to add this y-intercept, or this x-intercept, whatever you want to call it. Okay, now I'm going to have black on this orange, but it's okay. All right, I found my y-intercept, and now I'm going to find my x-intercept. The x-intercept is when y equals 0. Okay, this is what factoring is useful for. So I'm going to just rewrite this with y equal to 0. And I'm going to factor out a negative x here. Okay, they have an x in common. Everyone always forgets that common factoring step. Factor out an x. If there's a negative in front, always factor out that negative. Here I'm going to be left with 3x squared plus 2x minus 5. There's a 0 on this side. And I'm finally just going to factor this area over here into 3x plus 5 and x minus 1. Okay, once I'm in factored form, I can easily find my x-intercept. For instance, right here, this one is x equals 0. Okay, this one is x equals negative 5 over 3. And this one is x equals 1. Okay, remember, it's always opposite this number over this. Negative 5 over 3, done. Positive 1 over 1, done. Okay, and don't forget this 0, very common mistake. Just notice that these are the same. The x-intercept is the y-intercept in this case because it's 0, 0. Both the x and the y are 0. But I have 2 other points here. I have x equals 1. So I'm just going to make this up over here. I'm going to call this 1, and I have a point there. And negative 5 over 3, that's just about negative 2. So I can call this negative 5 over 3. Okay, so these are points so far that I have on this graph. 3 points on the x-axis. Okay, next. My critical points. So number 4. I need to find out when my derivative is 0. So I'm going to find my first derivative of this function. That's going to be negative 9x squared minus 6x plus 5. Okay, and I have to factor this because I want to figure out when this equals 0. So I'm going to factor out a negative, and simple trinomial factoring, 9x minus 5 and x plus 1. Okay, so my answers are opposite this over this, 5 over 9, and x equals negative 1. So what's this tell us? These are potential max and mins. This is when the slope of the tangent on this graph is 0. So this is a turning point this way or a turning point this way. Okay, or it could not even be a turning point if it's a cubic function. Okay, so 5 over 9 and x equals 1, negative 1. Okay, next. Why aren't I figuring out whether they're a max or min? Because since I have to find the second derivative anyways, I'm going to try to use the second derivative to help me understand whether these are max or mins. Okay, because I don't know if they're max or mins yet unless I figure out the intervals of increasing or decreasing with my decision table. So let's avoid that for now. I'm going to show you how the second derivative can help us do that. Okay, now I'm going to find the derivative of this. This is negative 18x minus 6. I think I made a mistake here. Yes, I did. Even though I factored it properly. This is a 4. 2 times 2 is 4. And this is minus 4. And I'm going to do the same thing here. Is I'm going to figure out when this equals 0. Okay, when does negative, am I taking out over here, 2? And this is 9x plus 2. Okay, so my answer here is just x equals negative 2 over 9. I like this point. I like these guys. I like these guys. And this guy. Okay, all these points are very important. Now, if I plug in these values into my second derivative, it'll tell me about the concavity. Okay, now what the concavity can help me is discover whether something is a max or a min. So for instance, I'm going to use the second derivative of 5 over 9. And my answer is going to be negative 14. So I'm plugging 5 over 9 into my second derivative. And because this is a negative number, I know that if my second derivative is less than 0, it's concave down in this section of the graph. Well, if the slope of the tangent is 0 and it's concave down, it must be a maximum value. Okay, so right away I know that 5 over 9 is a maximum value. Okay, I'm going to do the same thing with this negative 1. Here's another slope of the tangent being 0, so I'm going to test it using my second derivative. Is it concave up? Is it concave down? Is it neither? Because that's clutch, right? If it's neither, it's not a max or a min. So I got to keep that in mind. I'm going to plug in negative 1. I'm going to get positive 14. This opens up. Therefore, it's a minimum. So I know that this is my minimum and this is my maximum. Okay, and we can figure out what those are. I can plug in 5 over 9 into my regular function and see what I get. Pick up a calculator. I know that if I plug in negative 1 into my regular function, I'm going to get 4. So at negative 1 and 4, or negative 4, sorry. Negative 1, negative 4, I have a minimum value. This is negative 1, negative 4. Okay, likewise, 5 over 9, if you want to change that to a decimal, you can, obviously. I'm going to plug that into my calculator, and I'm going to get, at 5 over 9, about 1.6. So this is 5 over 9, 1.6. Again, however you want it to look, make it look like that. Okay, now, I already have a general idea of what's happening here, right? I can pretty much connect these dots and get a pretty accurate representation of this function. The last thing you want to look for is a point of inflection. When is this going from concave down to concave up? When is that point happening? Right here. Wherever your second derivative is 0, this is an inflection point. So if I plug this number into my function just to see where it is on the graph, I'm going to plug in negative 2 over 9. My y value corresponding to this is going to be about negative 1.2. Okay, so my inflection point is going to be at negative 2 over 9, a little this way, and negative 1.2, like right here somewhere. So now I can connect my dots, see where I'm changing from concave up to concave down. Sorry for that little bump there. And I have my graph. Okay, I used all the skills I had. Might look like a lot. I guess it is. And I can graph pretty accurately. Okay, again, we want to use the first derivative and the second derivative very rigorously. Okay, find these points, plug them into your second derivative, understand the concavity, understand the inflection point. All these things make a beautiful curve sketch. Okay, so next we're going to get into doing this with a rational function, which could be a little more complicated just because of the asymptotes and the domain not being XER. Okay, so next we're going to do a rational function right here. So we're going to use the same algorithm. This example is going to be a little cleaned up. I'm not going to be finding the derivative here. We know how to find the derivative, so I'll leave it in your hands. Instead, I'll tell you what the derivative is. And then I'll explain some things of what we did and how we can kind of save time in complicated scenarios. So, first of all, my domain. My domain in a rational function is a little more complicated because, first of all, I need to factor this. So I want to rewrite this in factored form because I can see my intercepts, or sorry, my asymptotes way more clearly. So I'm going to factor this denominator. And now I know that x can't be negative 1 and x can't be 2. So my domain is XER, but x can't be negative 1, x can't be 2. So what's this mean? These two things are my asymptotes. At negative 1 and at 2, I have vertical asymptotes. Okay, so at negative 1, please draw your asymptotes using a dotted line. It's going to save your life. Okay, so this is at 2, and this is at negative 1. Okay, so those are my vertical asymptotes. So right away, I did domain, I did asymptotes. Okay, now let's get to, this is actually 1 and 2. 3, intercepts. Okay, the x-intercept is pretty straightforward. If I want to find an x-intercept for a rational function, you just look at the denominator, or sorry, the numerator on top. So the x-intercept is when x minus 4 equals 0. This is when x equals 4. Okay, so at 4, oh, I didn't have terrible scale, but it's okay. I'm just going to put a 4 here, and I have a point there. I lied. I'm going to erase this because that's unacceptable. Okay, so I'm going to put -1 a little closer. I'm going to put 2 here. And now this 4 makes sense. All right, so I changed my asymptotes. I want to find my y-intercept now. Y-intercept occurs when x equals 0. So just plug in 0 into the x. It's pretty much calculator work, or mental math, I guess you can say. And this is when it is 2. If I plug in 0, I'm going to get -4 over -2. 2. So the y-intercept occurs at 2. I can call this 1, I can call that 2. So I have this point, and I have this point at 4. Intercepts, done. Next, critical points. I'm going to tell you what the first derivative of this is, right? I'm not doing quotient rule. It's going to take up my whole whiteboard. You can do it on your own time. I'm pretty sure we're all stars at quotient rule already. So my first derivative is -x squared plus 8x minus 6. You can do this on the side. Pause the video and verify this. You always want to keep those skills sharp. Okay, so this is my first derivative, and I'm interested in finding when this equals 0. So like a rational function, this is just when my numerator is 0. Okay, I can factor that. I can common factor it, trinomial factor it. You have to do whatever you have to do to factor this and find zeros. If it's not factorable, yes, we have to use quadratic formula. Okay, so if we use the quadratic formula here, because this is actually unfactorable, we're going to get our x values to be 4 plus or minus root 10. Okay, using the quadratic formula. Now, if you want to change those to a decimal, please, by all means. 4 plus root 10 is 7.2. 4 minus root 10 is 0.8. Okay, so I can plug in these values into my original function and figure out their y values. So these points are going to be 7.2 and 0.1. Next one's going to be 0.8 and 1.5. So these are potential max and mins that I really need. These are critical points. The first derivative equals 0. So I want to plot these points. I plotted one already at 0.8, okay, and 1.5. And the next one's 7.2 and 0.1. Horrible scale again, but it's okay. I'll be able to explain it. Now, the previous example, we used a second derivative test for the inflection points. So we're done this. And just to see the concavity, to see if it's concave up, concave down, max, min. We used it because we were going to use it anyways. In this case, do I really want to find the second derivative of this disaster? If you did this on the side, you pause the video, it's pretty annoying to find the first derivative of a function like this. I mean, I'd rather not if I had to choose. So I do have to choose. So I'd rather not. I don't want to find the second derivative. I'm going to use these points here. And I'm going to figure out whether this opens up or down. Okay, so how can I do that? I'm going to go back here for a second and just remind you that when you have a rational function, when the denominator has a greater power than the numerator, we always have a horizontal asymptote at y equals 0. Okay. I'm actually changing gears here a bit. I decided to redraw the graph just so you can get a better representation of what's happening in the past few minutes. And I graphed all the things that I really need to graph, like my 2 intercepts, my 2 vertical asymptotes, my horizontal asymptote. I didn't really graph it because that black line is there. And my critical points. So I want you to remember that critical points are not only when the first derivative is 0, but it's also when it's undefined. Okay, so these values, these asymptotes are critical points. So if I'm finding intervals, they have to be between every single critical point. For instance, from -infinity to -1, from -1 to this is 0.8, 0.8 to 2, 2 to 7.2, whatever it is, 7.2 to infinity. So there's a lot of intervals here, and why I need to test all those intervals is just to see if the function's increasing or decreasing. Okay, so for instance, I can plug in a number into the first derivative. Okay, and just a reminder, the first derivative is here. So if I plug in a number in this interval into the first derivative, I'm going to get a negative answer, which tells me that this is decreasing, and I know this is going to be approaching y equals 0, and this is decreasing. okay, because it's a negative number. If I plug in a number between -1 and 0.8, I'm going to get a negative number, like for instance 0, plug in 0. And because I got a negative number, I know that this is also decreasing to this point. Next, I'm going to plug in a number after 1 but before 2, let's say 1.5, and I'm going to get a positive number, which tells me that this is increasing after this point. This just right there told me that this is a local minimum. Okay, so I'm going here. This point right here is a local minimum. Okay, make sure you draw arrows. Next, I have this interval between 2 and 7. Don't use your intercepts as intervals. It's only critical points. Intercepts are not critical points. Okay, so between 2 and 7.2, pick 4, pick 3, pick 5, whatever, plug it in, and I'm going to get positive. So my function is increasing, and I know I got to go through both these points. So it's increasing and then turning and going to the 7 and continuing forward. Now, a little tricky here because it's hard to see, but after this 7, if I plug in a number, I'm actually going to start decreasing. And I'm going to decrease as I approach my asymptote forever. So that's how it's kind of going to look. Okay, so those are my intervals that I've just described. I will make a decision table in probably a review lesson or something, just so you can see it in a table. I'd rather you understand it just by checking intervals from your graph, because you have to create the graph anyways. Now, let me talk about the second derivative one last time, and then we're done. I want you to take a look at this thing that's happening right here. So there's actually should be another inflection point out here somewhere that changes the concave down to concave up. Okay, this happens like maybe around here somewhere. And if I find the second derivative, I figure out that the second derivative is 0 when x, I think it's like 10 point something. Okay, so we do use the second derivative to find that inflection point, but it's going to take so much time to find that second derivative that if I just understand that there's a horizontal asymptote at 0, I got to go through this point, I can kind of just figure that out, right? It's not, the juice isn't worth the squeeze by finding the second derivative here just to find an inflection point out here, right? There's a minimal thing happening here. I kind of understand it in different ways, so I don't want to put in that work. So remember, all these skills are things we know, and you want to basically use as few as possible to get the best representation of this function on a graph, right? The faster you can do this with the least amount of work, the better. But you also don't want to leave out any information. For instance, I left out this information, and I think that's worth it, okay? So by practicing, you'll see what's worth it that you can leave out. And it's generally when there's irrational functions, if you can avoid doing the second derivative, you try to figure out another way to do it. Okay, so this is curve sketching for a rational function.